All right, start out with this first molecule. And this one is the NO2Cl. This is the one I was telling you about the other day that formal charges doesn't work. Okay. And like I told you, this was accidental about last year's exam. This was not intentional. I had the structure in mind, the correct structure, and then some students, I guess it was a couple of years ago because, well, I guess it was multiple choice, but some students came to me, talked about it, and they say, I did this formal structure, and I got all formal charges of 0, and and it's wrong. So we're going to take a look at this one. And this is one of those cases where I told you when you don't have just a single central atom and everything around it, sometimes well, I guess this one. So you have two options here. You can draw it kind of linearly, say that 10 times fast, and you'll get really good formal charges. So how many valence electrons do we have? Let's go through this. "24, right? Megan says 24, that's correct. All right, so now we got to build the structure, but it will answer the rest of the questions. And, nitrogen, right? It's going to be our central atom for the most part. And if you do something like this, you're always looking for oxygen to have 2 bonds, right? Nitrogen to have 3. That's just guidelines, of course. There's exceptions to all these things. But if I did something like this, right? My nitrogen's got 3 bonds. Both my oxygens have 2. And of course, chlorine's a halogen. It's got its 1. This looks pretty good. And this was the structure that a bunch of my students drew and said, hey, what's wrong with this? And there's absolutely nothing wrong with it from your knowledge base. So that is 24, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, I need a lone pair on the nitrogen. And now I just put dots everywhere, so that's really confusing. I'll do that over. I should have used a different color, just check marks or something, but we do need a lone pair on the nitrogen to complete that octet. Now we've got our 24. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that's what we said, 24 electrons. We're good. Look at my formal charges. They're all going to be 0, right? Get good with this. Get fast with this. Anytime you have a halogen with 1 bond, its formal charge is going to be 0. Doesn't matter if it's chlorine, fluorine, bromine, because it's 7 minus the 6 and half the 1, it's going to be 0. You don't have to do this every time. You get familiar with it. You see a halogen with 1 bond, boom, its formal charge is 0. And you should know by now, oxygen with 2 bonds and 2 lone pairs is 0. So these are all going to be 0. And then nitrogen is 5, and it's got 5 minus 1, 2, 3, 4, 5. It's the easier way to do it rather than the formula, quite frankly. I just do that. I just go 1 for each bond and 1 for each dot. I didn't bother with the formula. And that's got a 0 too. Beautiful structure, right? It's just not right. And like I said, this was not intentional. So all the students that put that, because your answers do change, obviously, got credit. What you start to realize is if you can draw condensed structures with branching, that tends to be more stable than structures that are just strung out linearly. Now, I mentioned the other day that hydrocarbons are structured out linearly, but they have tetrahedral with alternating angles, so it's stabilized a little bit that way. So here's like, a hydrocarbon. This is butane. And that jaggedness kind of reduces the repulsions, and this is stable, but branching would make this more. There's other compounds that have 4 carbons with hydrogens that are branched that are more stable than this. It doesn't mean you can't have a linear compound, right, that's not stable. It just means that in this case, for this compound, doesn't form like that because the other option, and even though the formal charges are not going to all be 0, the other option actually is more stable for this compound. So if I'm going to draw another one, what's it going to look like? What's my central atom going to be? Nitrogen, right? So instead of stringing it out, why don't we throw the oxygens around the nitrogen, right? And then we could throw the chlorine off of that. We can do that. We can still have a double bond, right? On an oxygen, but you start to realize, okay, you can try this. So what do we have? What do I say? 24 electrons, right? So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So instead of doing that, let's put the chlorine off the nitrogen also. It's going to create 4 bonds, which is not, always what you want, but it's okay. You wind up with this. So now we've got, let me count with this. Oh, wait, I forgot to do electrons here. And I need another pair here. Now I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's the correct structure. Now my nitrogen winds up being +1, and the oxygen winds up being -1 over here, right? The other oxygen's 0 and the halogen's 0. This is the structure NO2Cl. Okay, it doesn't exist like this. That's all there is to it. So this is a learning exercise. Like I said, I'm not going to throw one of these at an exam. If I did, like the same thing that happened to happen accidentally, you would get credit for this. But because now the answers change, of course, because there's a little bit different structure here. So sometimes that branching is much more stable. The other thing you'll start to learn when you take organic, like the way these electrons with pi electrons and bonding and anti-bonding electrons, you'll start to get a feel for structures a little bit and how the electrons kind of would be more stable in certain positions, things like that. And maybe something like this down the road, you would look at this and realize this is going to have a central nitrogen. You'll be dealing with carbon compounds exclusively in organic pretty much, but you get the idea. All right, so now we can answer the questions. How many bonds to the central atom? And of course, a W count is 2, so it's 2, 3, 4 bonds. How many total lone electron pairs in the molecule, total in the molecule? So now you got 1, and it says pairs. Read it carefully, very carefully. Some will say on the exam, pairs. Some will say electrons. How many electrons are around the central atom? Some will say electron pairs. Okay, just attention to detail. Just read the question carefully, answer what they're asking. All right. So what are we doing here? Electron pairs. So 1, 2, 3, 4, 5, 6, 7, 8. Lone. So we don't want the bonded. That would be the 8, right? Did anybody try this structure before today? I'm just curious what you get.
I got
the correct one. Cool. But the thing is, from what you guys know, the linear one has 0 formal charges. You might want to think in that, that's the problem here. Okay, so based on the correct structure, what's the electron domain or pair geometry? Trigonal planar, right? Trigonal triangular planar. Because there is no lone pair. You only got 3 regions. So I drew it as T-shaped really, but, well, not really, but kind of, sort of, not really. No, it's not. Whatever you call that, but, whoops. So there's no lone pair here. So basically it would be like this, the structure. So that's the trigonal planar, the triangular planar. What's the molecular geometry? Same, right? No difference because all of them are bonded. Okay, we didn't cover this, so you're not responsible for this. Sigma and pi bonds. I covered this in the past. I didn't cover it this year. It's real easy in case you come across something. I'm not going to explain what sigma and pi bonds are. That's not easy, but just counting them is easy. Any single bond is a sigma bond. Okay, and any higher order bond is a double bond, but the single bond is still the sigma. So these are sigma. That's sigma, that's sigma, and one of these is sigma, and then the other one is a pi bond. So if you have a double bond, you have one sigma and one pi. If you have a triple bond, you have one sigma and two pi. That's all. And single bonds are just sigma. Like I said, I don't think that's going to be on the final exam. We pretty much decided not to include that kind of stuff. So, but last year I taught sigma and pi bonds. So that would have been what then? Would we say 3 sigma and 1 pi, right? So that would have been B. What's the formal charge on the central atom? And that's why, the structure up here is a little confusing because there is no real central atom. But when you draw it like this, obviously there's nitrogen. What's the formal charge? We already did that, right? It's +1. What's the hybridization on the central atom? sp2, right? Did you say sp3? Yeah, remember, just count the regions. This, I don't know why this happens all the time. So you get 3 and you think 3, sp3. But no, it's sp2 because you effectively got 1 s and 2 p. That's your 3 regions. This is the best way to think about it. Accounting wise, it doesn't make sense in terms of what's going on bonding. You don't have 1 s and 2 p's. No, just like electron domain geometry, right? This is linear, 2 regions. That's it. It doesn't matter that there's double bonds. Good question. Yes, sick. So double bonds, you treat it just regions. That's why I like, or domains. That's why I like that better than electron pair geometry. I like electron domain geometry. You think of that, they're in the same domain. They're not really necessarily when you get to molecular orbital theory. But anyway. And I think that was it, right? So sp2 for that one, that molecule. Questions? Oh, a radical, you mean?
Yeah.
It's still considered a region.
Okay.
Yeah, it's got to have a region to occupy, so you got to think of it having an orbital there. So,
Okay, so it would be like 1 along with like 1 pair.
yeah, so let's see. Oh. Whoops. Right? So doing steric numbers with just 2 molecules, but anyway, this is a region, this is a region, and this is a region. Other questions? Yeah. Yeah, you won't have one like that. I'm trying to think of an example of three. I think I might even have one that I picked out for today. Was that 1, 3, or 2? No, that was, never mind. It was 3. So I can't think of an example right now off the top of my head. So I just use that to just say that if it's a chlorine dioxide, 19. Let's try this one. "17 electrons, right? That would give me 16 if I put octets around. With chlorine, I'm only having 2, 4, so we had a double bond here. Resonance. So you get 8, 16, 17. Okay, this is kind of what you were asking, right? Is that right? So steric number would still be 1, 2, 3. So sp2. What I wind up with here, 0 formal charge, -1, 1, 2. What is this? This is wrong in the structure. Hang on. 2, oh no, it isn't. That's fine. No. It's 17. This can't be right. What am I missing? It's got the formal charge on chlorine is so high. Still works for the.
I think the number of valence electrons.
Oh, did I count it wrong?
I think it was 19.
No, thank you. Maybe something simple like that. Yeah. Did I do that? 12 and 7, 19. Thank you. It's 19. So now we've got this 2, 4, 6, and we got expanded octet with that. So now you have a 1, 2, 3, 4, 5, 6. You get a +1 on the chlorine, -1. Thank you. Yeah, but still works for the steric. What we said about the steric. So now, so now you've got, yes, now you've got this here, right? So you've got 1, 2, 3, 4 sp3 hybridization instead of sp2. But you do have to count. Oh, you guys aren't seeing that. Sorry. You guys have to count a single electron as a region because it does need a region. What happened? Is it buried somewhere? Oh, there we go. You do have to count. So it's sp3 now, hybridization, because you've got 4 regions. You got the 2 oxygens, the lone pair, and then the singlet oxygen has to have another region to occupy. Okay, we're back to the exam or the review. What exam are we on? Yeah, my mind's on flying to New Mexico, not here. Sorry. All right. It's the first time I've been on a plane since the pandemic. I'm a little skitsed, a little freaked out about that. But I got my N95 mask and I'm vaccinated, so I should be okay. All right. Considering the following molecule. Now, this one was intentional. And that is, you can draw it two different ways, but all your answers are exactly the same. So it doesn't matter which way you draw it. This is what I was talking about the other day when I was trying to show you examples of alcohols and ethers and things like that. So whichever way we draw it, and if people tried this, did anybody try it? What'd you get? Where's your oxygen? Okay, so you drew the alcohol, very good. She drew the alcohol with the OH group off of one of the carbons. Anybody draw the ether with the oxygen in the middle? And Hersha? And the two methyl groups hanging off of that, they're both correct. You get the same answers either way. So, what's our valence electrons? What is it? 20, can't hear. 20 what? Somebody? You got 16? No. Carbon is 8. And 6 is 14. And 6, 24, right? Hello? 4 plus 6 is 16. 20, thank you. 20. All right. All right, let's draw it before we can answer the question. Obviously, whether it's polar or not. Either one of those will be polar. They're both going to be polar. What you have to realize is that your Lewis structure won't always be clear, demonstrating polarity. Okay? You have to realize where the lone pairs are and say to yourself, okay, that Lewis structure is right, but what's my geometry really? Okay? So, you got a carbon, right? And you got another carbon. And carbon's like 4 bonds, so it's not unusual to think of something like this, right? Of course, you can't put that last hydrogen there because then you'll have nowhere for the oxygen. So you go like this, and you put the hydrogen off the oxygen. And what's your first name? What is it? Shakira? So Shakira, this is what she did. And this is correct, right? This is an alcohol. Okay, and I can draw my 2 lone pairs here. That's not a problem. And what do we got? We have, what do we have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We're good. That's an alcohol, an OH group hanging off of that carbon compound. Now, it's going to be tetrahedral around both carbons, but you realize, take this one right here, just look at this here. And effectively, it's bent around this, right? And you got these 2 lone pairs up here. This is going to create a dipole. So it's almost like water. The only difference is instead of 2 H's, we have an H and a methyl group. So think of it like that. Here's my water molecule, right? Replace one of those H's with a methyl group. In organic chemistry, just put an R there. You can put whatever you want there. You can put just some sort of organic structure there. Doesn't matter. Okay. Now, if that was very polar, if R was very polar, I put R stands for organic group. Okay. But if you put something like a fluorine there, well, that's going to create a problem, right? In terms of our polarity, it'll still be polar, your dipole being a slightly different direction. Okay, so just think of it like water. Just having this CH3 group down here really doesn't impact much because carbon and hydrogen's electron activities are close. So this methyl group is not going to affect this dipole here. So that's still polar. You see that? Questions? So let's do that one now. Yeah. Let's put the oxygen in the middle. Okay. And you're going to see what's going to happen. You have 2 methyl groups hanging off of the oxygen. That's all. For the ether, let's do it like Hersha did it. I'm going to draw the actual, more structurally correct. right? That's the ether with the oxygen in the middle. Still polar, right? Got the electronegative oxygen that's pulling that up there. So all the answers wind up being the same. We got the 24, it is polar. What's the formal charge on the oxygen atom? Doesn't matter which structure you drew, oxygen's got 2 bonds and 2 lone pairs, so its formal charge is 0. What are the bond angles around the carbon atoms? Doesn't matter how you drew it. What are the bond angles? 109.5, that's the standard for tetrahedral, right? What is the hybridization of the oxygen atom? Doesn't matter which one you drew. sp3, because we got 1, 2, 3, 4 regions, and therefore sp3, 3p and 1s is the way to kind of sum it up and think about it. Questions? If what was the different atom?
Like you have totally different. Sorry.
Okay. Symmetry, right. So go look at that slide that I gave you that tells you the ones that are symmetrical, and if all the attached atoms are the same, then it won't be polar because all the dipoles cancel out. So it would be nonpolar because that's a symmetrical molecule with all the attached the same. If I take one of those chlorines off and put a hydrogen there, now you're going to have a dipole. Other questions? Good. Copper 2 nitrate. Now you won't. Yes, I'm sorry. Did you have a question, Annie?
Like always, like the number of the stericum?
Yes.
-1.
Not -1. It's just the steric number, right? So the steric number here is 1, 2, 3, 4, the same as it is for water. They both have the same steric number 4, right? And they both have the same hybridization, sp3. So it is. Steric number is the the hybridization is the steric number. Just those electron domains. Doesn't matter if they're bonded or non-bonded. It's just the domains. Count those domains. I'm trying to think of how I asked questions on naming. Did I ask questions on naming in the exam? I didn't. I just realized that. I guess I did on the quiz. The exam's already made up. And I told you the breakdown the other day. It was only off by 1 question. I think I gave you 26. And there's 1 less bonding question. I think I'd said 5 on bonding. And there's only 4. Everything else was the same. So there's no questions on naming. Let's do this anyway. Copper 2 nitrate. Which one? Which one? E as in Eric. Agree? Yes, we got copper 2, so it's copper 2. And nitrate, you have to know the polyatomic ion is -1. So you need 2 nitrates to equal that copper 2 plus. You'll need to know this stuff for a final exam, so we might as well do it. So you got a metal there, so you're using, that's where we're using the Roman numerals, right? Because copper could be +1 or +2. There were a couple we said that only have 1 charge. Silver was one of them. You don't ever need Roman numerals with silver. It's always +1. Zinc is always +2. All the rest, pretty much, of the transition metals, you're going to need to use numbers. What's the correct name for P2S5? So, A, agree? Right? Diphosphorus pentasulfide. Using the Roman numerals, that's only for metals. That's nonsense. Phosphorus hexasulfide, no, because there's 2 phosphorus and there's not 6. And potassium sulfide, no, it's not even potassium. If you choose A, I have to shoot you. I have no choice. If you think phosphorus is potassium at this point, we're in trouble. All right. I guess I shouldn't have said that. I'll get in trouble. All right. Which of the following is or a radical as an unpaired electron? You put B as in boy,
No, B is not.
D as in dog. Agree? Let's take a look. So we've got, nitrogen's odd. It's 5. And oxygen is 6. That's going to make an odd number. So we know it's A. But then we've also got one with 2 nitrogens, which is 10, which is okay. So it's not going to be C. But then this one has got 6 and 6 and 12, 17. But that's going to be odd also, right? So both of those are radicals. So that we have, what'd you say, D? So both A and B, right? So D is the correct answer. They're both radicals. The next 2 questions would fall under those like bonding category for the exam that I mentioned. Things like electronegativity, things on bond strength, the character of the bond, stuff like that. Which of the following will have the smallest, weakest lattice energy or bond strength, if you will? What's that? A as in Albert? Agree? Yes? Okay, let's take a look. Bromine's pretty big. Let's see. We've got, oh, I'm looking at the wrong question. I'm looking at 18. So CSI. So CS is way down the bottom left. I is bottom right. They're both pretty big. They're both charges of 1. So it's a good choice. So we got CS is 1 plus and I is 1 minus. We have strontium, which is +2, and this is +2 minus 2. That's going to have a pretty strong bond. This is +2 minus 1, plus strontium's even smaller than cesium. Remember, we're looking for the big atoms with a low charge. That's going to create weak bonds because the bigger the atom, the bigger the separation. The bigger the separation between the nuclei and the electrons next to it, as opposed to something small like that, right? Then you got a pretty close. So we're looking for big ones that have low charge. So rubidium, pretty good size, but it's bonded to sulfur, and it's also smaller than cesium. And then cesium and chloride versus cesium and iodide, and chlorine smaller. So Annie's correct with 17 being A. Which of the following, we good on 17? Which of the following would have the most polar ionic character? I use those kind of synonymous because remember I told you it's a continuum. There's no real breakdown. You have at one extreme completely polar, the other extreme completely ionic, but most things fall in the polar covalent really. And this idea of 0.4 being some sort of cutoff, I don't even think of it like that. It's a complete continuum. So just which one would lie most to the right? It's kind of like on my little thing here. Which of these? You do have electronegativity chart to look at. but you can use the same type of thing. Or you can just use the trend, you should be able to answer. So we've got copper and bromine, right? And we got copper and chlorine. Copper's, transition metals don't follow the trend quite as much, but they're certainly higher electronegativity than the metals all the way to the left, right? And you're looking for large electronegativity differences. That's what gives it its polar ionic character. So I'm going to get rid of these two copper ones. And then it's a matter of choosing between cesium and potassium. Well, potassium's further up, so it's got a higher electronegativity. So I'm going with cesium. So I'm getting rid of potassium. And then once again, same thing. I want the one further up on the right. So basically, you're choosing this, right? Furthest down left, highest up right, because that's going to be the greatest electronegativity difference. You don't really even to look at the numbers to answer this. So it should be the cesium chloride. Okay.
You said it would be cesium chloride? Okay. You said it would be.
Oh,
And I actually had one quick question on 17. Does the size of the atom increase as you go down the periodic table?
yes.
So wouldn't chlorine actually be smaller than iodine?
Yes.
So would the correct answer be BSCl?
No, you want the largest ones because that creates the weakest.
Oh, I see what you're saying.
Yeah, sometimes you get these questions, you can get easily wrapped up inside your head and twisted around. You might be comfortable with the chemistry, and next you read it, and then you always go back and read it and read it again. Make sure you're answering it right. We good? CLI3. That's our molecule. Okay, we're going to figure out how many valence electrons to draw the structure. So how many do I have? This one's easy. 28 because they're all in the same group. 7 times 4, right? 28 electrons. We don't need that for an answer, but we'll need it to actually do our structure. 20 electrons. What's the central atom? Chlorine, obviously, it's listed first. And it's got the 3 iodine around it. So, whoa. So I'm just going to go. I don't know why I'm squeezing it here. I got this whole page. Okay, so if I do 8 times 3, that's 24. What do I do with the other 2 pairs? Stick them on the chlorine, right? Chlorine's down low enough in the periodic table. It's in group period 3. So we can take on the expanded octet, because this is an expanded octet, because it has what? 2, 4, 6, 8, 10 electrons in its valence shell now. Okay, so now I think we can answer the questions, right? How many bonds to the central atom? Well, that's clearly 3. How many lone pairs around the central atom? 2. You're asked for pairs. The 4 is there. So if you read electrons and you choose 4, what's the electron pair or electron domain geometry? Trigonal biopyramidal. It's got the 5, basically steric number 5. That's the trigonal biopyramidal. What's the molecular geometry? T-shaped. When you pull off 2 axials, right? Picture that model I was bringing in the other day. And I never looked and saw where my models are. They're in my office. I forgot again. T-shaped. You'll wind up with, and you can see that almost the way I've drawn it. There's your T. What's the hybridization on the central atom? SP3 what?
No,
Oh, SP3 dog. SP3G, right? Got 5 regions. 1, 2, 3, 4, 5. Same as the steric number, so that only goes up to 4, 3, and 1. I need a D to get me. And we did figure out why the book stopped and didn't cover D, because some of the things I even mentioned, it doesn't work that great. The model, because you've got 5D you've got 5D orbitals, and it's not using all the D orbitals the way it uses all the P orbitals. So that model doesn't really describe D orbitals very well for bonding, so they decided to stop there. Does the molecule have polar bonds? Yes. I mean, that's another way of asking, like, is the electronegativity between I and Cl different? Okay. And they're different enough because Cl's 3, right? Right. Cl's 3, bromine, I don't know. It's probably 2.5. It's probably just really considered polar based on that breakdown, but, you know, I'm interested in recognizing electronegativity difference, not memorizing 0.4. That's all. If it was 0.1, it would still be polar, right? It's just very weakly polar, and someone decided to make the cutoff 0.4. That's all. All right. So yes, is the molecule polar? Yes, right. You've got an odd shape here. You got a T shape. They're not canceling each other out, right? Plus, you got those lone pairs over there. This will definitely be polar. It's not like trigonal planar, even though it's only got 2 attachments. It's got those lone pairs, which creates this T shape that makes it polar. Questions? All right. Yes, Andrew. Did you read number 12? Read you 12? What was 12? What are the bond angles around the carbon atoms? Both are the same. Okay, so this is really what you have here is tetrahedral. You've got a carbon. This is really no different than methane, right? You see it? And that's just tetrahedral. The fact that it's bonded to an oxygen on one end, it doesn't matter. It's still tetrahedral. And that's what's nice about Lewis structures. You can build larger structures once you learn the simple Lewis structures and putting them together. Just like we saw here, that this is, this is bent, this is tetrahedral, right? That's tetrahedral, and this is angular or bent around those lone pairs. So you've got these shapes that are kind of bound together. No.
No.
So you don't have your carbon having 4 bonds. It happens, but it's rare. It's like the one on Smart Work there, but they should have put that bond on there. I don't know why they did that. But no, if you have an opportunity to make, so she drew it like this. Right, the carbon, oxygen, carbon, and then how many?
Because I still filled the octet.
You still filled the octet, but
These are
hydrogen's everywhere,
20,
right?
20 electrons.
Yeah, but what's your formal charge on your carbon? Right? Just the way she drew it, which she's got her octets, she's got the right number of electrons, but her formal charge on carbon now is 4 minus 2, 3, 4, 5, which gives you a negative formal charge. When you've got an oxygen sitting there, that's electronegative. And you also have your oxygen with 4 bonds, right?
Oh, yeah.
You also have oxygen with 4 bonds, which is kind of a no-no. 3 you can get to, but 4 is pushing it. And if you look at the formal charge on oxygen, then it's 6 minus 1, 2, 3, 4. It's +2. Not a great structure, no offense. So we just what's your first name? Maggie? Yeah, it's a good try, and you're thinking that's good. And that's the more mistakes you make like this, the more structures you do, you more you start to realize, oh yeah, carbon, I want to have 4 bonds for carbon. I don't want 4 bonds for oxygen. Let's switch that around. All right, other questions. I've got a couple picked out. I think this one was assigned in the back of the book. The others are not assigned. It was one of the, it was like draw the low structures to these 4, and this was one of them buried towards the back, like one of the higher numbers, but let's take a look at it. ClO3. We're going to do the lower structure, then we'll do the electron domain, and we'll do Vespri. Give it a shot. Take a second and scratch it out. How are we doing? How many valence electrons? What you got? Usually double bonds. How many? We got 25. need that many double bonds or triple bonds? Okay, so chlorine with 3 oxygens, right? That's easy enough. We've only got 25 electrons, so we can do 2, 4, 6, 8, and have our 24. And put the 1 there, and it's 25. And we could say we're done. Formal charges on all the oxygens are -1. The formal charge on the chlorine is what, though? +3, right? So let's try a double bond then, right? And that'll drop one of the formal charges on oxygen to 0 and change my formal charge on chlorine. So I'm going to get rid of this bond here, this pair here, and put a bond here. Now I've got 0, still got -1 and -1 here. And now I've got 7 -1, 2, 3, 4, 5 +2, right? Why not do it again? Right? Why'd you have a triple bond? That's, I guess, kind of what my question was. And 2 double bonds, right? You had, yeah, so let's do 1 more double bond. If you go about it methodically like this, whoops, let's get rid of this here. We're gonna get rid of that -1 now also. Double bond here. We now have a 0 over here again. Whoop. And what's chlorine now? 1, 2, 3, 4, 5, 6 +1. Let's do it again. Why not, right? It's going to give us a 0 and zeros on all of them. And chlorine can take the expanded octet. Let's see. It's funny because, no, we have a radical though. Some reason I think, why do I think that's wrong?
So if it's an odd number, there can be like a lone electron on a central atom.
Yeah, it could still be a radical because it can expand the octet, but this is, whoops. For some reason, I think this is wrong for some reason. I thought it had resonance, which means it would only have 2 double bonds. This works formal charge wise though. Because now we have, now we have 0, right? Everywhere. 1, 2, 3, 4, 5, 6, 7. -7 is 0. Yeah, there is, but of course you've got 5 d orbitals. So that can take a lot of electrons. So who has can easily, for me, Google Lewis structure of chlorine trioxide. I could have sworn there was resonance, and it's, and you go over what can have the expanded octet again. Anything in the 3rd period down can expand its octet because it's got d orbitals available to it. So third period on the periodic table and beyond. Yes. Yeah, what's it look like? Careful where your source is, though, because it doesn't always work. I found lots of wrong Lewis structures online.
One looks like the one we did, and another one looks like super long on the opposite and 2 on the other.
Yeah, see, this is what I thought. I thought there was resonance. Oh, no, that's the ion. That's 26 electrons. So one, 2, 3, 4, 5, 6. Yes, that's got an extra electron, so it's not a radical. So the formal charge on chlorine there is 1, 2, 3, 4, 5, 7, 0. You see the difference because it's the ion. You got to be careful what you're looking at. Mine was not the ion. These are all the ions. That's common, the chlorate ion. That's one of the ones you're supposed to memorize, actually. What's that? Double bond on all the oxygens. You found it?
And it's
Okay.
.gov.
And it's what?
It's .gov.
Oh, because it's a oops, I'm sorry. Used a lot as a disinfectant, chlorine trioxide. Okay, so we got it right. Yeah, be careful because that's the ion there. So we're okay. And we followed the formal charge. The formal charges usually work when you have molecules like this with one central atom built around it. It's when they start to get strung out with multiple atoms that the formal charges doesn't work great all the time. All right, so what's the electron domain geometry? What's that? Right, you gotta count that. 1, 2, 3, 4. So it's tetra. And then the molecular geometry, trigonal pyramidal, not planar. Just picture the tetrahedral and pull one off. It doesn't become planar, right? Not to be confused with trigonal bipyramidal, which is the 5 steric number. It's like ammonia, right? Nitrogen with 3 hydrogens and a lone pair, trigonal pyramidal. Okay. Another one I got is, I chose tough ones specifically, so if you can get to this point of do these tougher ones, and there'll be some. I had a question after class the other day. Will most of the low structures be, the simple molecules with one central atom, and that's it? You'll have both. Okay. There'll be some with larger molecules, like we've done today. Se2O, so it's selenium. No. Chat question is trigonal pyramidal the same as T-shaped for molecular geometry? No. Get it? Where do you go?
still have the formal charge of the -1. Oxygen is more electronegative than selenium.
Not easy. See, a lot of you putting oxygen as the central atom. "18 electrons, right? We run into some problems with oxygen as the central atom. Because you're going to do this. Okay, you're going to need double bond because you're going to only have 16, only got 2 left, right? That gives me what? 18, and I don't have an octet on oxygen yet. How did you do it? The original one? Oh, yeah, okay. How'd you get the octet on oxygen? You just throw another pair?
Yeah, I did a double bond and then I just put like a lone pair on there.
Okay. So you see, you run into problems, right? 2, 4, 6, 8. That's 16. Put a lone pair on there. Okay. Now the problem is what? Selenium's formal charge here is -1, right? Oxygen's is what? 2, 3, 4 +1, right? And selenium 0. Well, oxygen's more electronegative. Also, if we take selenium, we can actually expand the octet if we need to, which is ultimately what the correct structure will be. That's 16, 18, right? We now have octets on everything. Oxygen is 0 in the middle. Selenium is 0 on the outside. The selenium in the middle does have 2, 3, 4, 5, 6, also a 0 formal charge. So you got all 0 formal charges, got all your octets. The only thing you violated, which is not a violation, is the expanded octet because selenium is in group 4 and it can handle an expanded octet. So this is the correct structure. So when you have something lower in the periodic table, it will often be, not always, but often be the central atom, especially when you got a situation like this where you can expand that octet. Questions? Good? Question? All right, I got another one. CN2O2. You tell me you know what the central atom is. Carbon. You got to go with that. Now, it's not a true central because you have, 4 attachments, but still, it is more I guess, I don't know. I guess you consider one of the nitrogen central too, but. Want that nitrogen, you want the carbon to get 4 bonds. You want the nitrogen to try to get 3 bonds, but you probably won't get both of them to get 3 bonds. You'd like the oxygen to have 2 bonds if possible, but not going to kill you if it doesn't. And there's 2 oxygens, so you might wind up with one without that. That often happens when you have multiple oxygens. You get one to a formal charge of 0. Should be shooting for the oxygens to be more peripheral. If they're further to the right. Let's take a look. You want carbon to be central. Now you can start doing this, but then you're going to have trouble with this other nitrogen and getting it the way you really want it in terms of bonds and things like that. So if you think about the oxygens can satisfy the nitrogen bonding, then you can do this like this structure, right? Thinking of the oxygens more peripheral, don't double bond them quite yet around the carbon because you need the nitrogen to get bonds. So by double bonding the oxygen, you're kind of losing a bond. And you're trying to get nitrogens to have, 3 bonds, right? Well, you say, well, Dr. D, you got that one nitrogen floating out there with 1 bond. Yeah, but we're not done. We're going to add some additional bonds to that because we're going to run out of electrons. We're going to need to. Because we only got what? We say 26 electrons. Our carbon doesn't have its bonding yet either, right? It's only got 2 bonds. It needs 4 bonds. But you don't want to put a double bond here because nitrogen's already got 3 bonds, right? So if we do this, now your carbon's got its octet, right? We could do it in order and finish these octets here, but we're going to realize we're going to need a double bond on one of these oxygens. And then we're gonna complete the octet there. So let's see, what have we got? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Carbon gets 4 bonds. Each nitrogen, well, the one nitrogen gets 3 bonds. The other one's actually got 4 bonds. The oxygen gets 2 bonds, but one's got 1 bond. You can't, those are just guidelines. You can't satisfy everything. You're looking at formal charges though. As always, this is 0 and this is -1. This is 0. This is 1, 2, 3, 4, 5. This is 0. So that's pretty good. The nitrogen is going to have a +1, right? 5 minus 1, 2, 3, 4. And that's okay because the oxygen's -1, that's more electronegative. Pretty low formal charges in 1. Okay.